Okay, let's wrap up our discussion on seismic loads. Earlier I mentioned how the location of weight in a building is important when designing for seismic loads. If you can imagine a tall building like this, if we place a large mass somewhere in the middle of this building, that mass will cause that floor to have a different response to the ground motion than the other floors. And that will cause additional stresses in the building. So having drastically different amounts of mass from one floor to the next is a seismic irregularity. This large amount of mass could be a mechanical floor or an indoor pool, etc. Next we have geometric irregularities, or setbacks, and we talked about that earlier. Next we have soft story. Soft story occurs when you have one floor that is drastically taller than another floor. If you can imagine this building subjected to seismic motion, this bottom floor is going to be much less stiff than the upper floors. This happens pretty regularly with buildings in cities that like to have a tall open lobby on the first floor and tightly packed offices or residences on the upper floors. Lastly, we have discontinuous bracing and weak story. Discontinuous bracing is when we change the location of a brace along a brace frame. And weak story is when we discontinue a very rigid lateral system like a shear wall before it reaches the ground level. And these two are similar to the upper two plan irregularities that we talked about earlier, as we are making the lateral system discontinuous, or we're creating a kink in the lateral force resisting system. And so these four are the ones that I would most recommend trying to avoid. The other ones we can and do deal with relatively easily. These four, on the other hand, are not so easy to deal with. We want the lateral force resisting system to have as clear and direct of a path to the foundation as possible. Of course, we can handle these irregularities when necessary, as with the sewer easement underneath the Mass Art treehouse. But if we have the means to provide a direct path to the foundation, we absolutely should. Now, let's talk a little more about the structural system itself and how it plays a role in seismic forces. So, do we want this structure to be more flexible or less flexible for seismic loads? Well, as we mentioned previously, a stiffer structure will have a higher inertia, and therefore will actually have higher seismic forces to resist. So with seismic forces, we actually do want to have some flexibility. If we allow the building to be flexible, more of the energy can dissipate as it moves and stretches, and we will have lower seismic forces. But of course, we cannot have too much flexibility, or we will run into issues with stability. Ultimately, it's not the earthquake that brings the building down, it is gravity. So if we allow the building to sway too far, gravity may take over and cause the building to collapse, even though our forces were actually quite small. So with seismic forces, we need to pay close attention to both strength and stability. And so we need to control where this flexibility, or where this stretching, occurs in our building. One of the ways we can control the flexibility of our building is with reduced beam sections. These are areas where we have purposefully reduced the steel section, creating a weakened area that will stretch under seismic motion. This stretching is referred to as yielding, and we'll talk more about that in the next video. And here you can see a real example of a reduced beam section. This area acts like a fuse, if you've ever taken an electrical course or looked in your electrical box in your basement. Although today, we typically use breakers, which are a bit different than fuses. But basically, with fuses, when electricity enters your house, you want to make sure that there isn't too much current flowing toward your valuable electronics that could damage their internal wiring. So we place a fuse in the electrical box, which is basically a reduced section of wire. And we know that this reduced section of wire will burn out first when a power surge occurs, preventing the surge from reaching more valuable wiring. This is the same principle with a reduced beam section. We know that the building will sustain damage during an earthquake, so we control where that damage occurs. That way, after the earthquake, we can go in and easily swap out these beams like a fuse in a fuse box. Now, this reduced beam section is a type of detailing that is generally only used in areas of high seismic activity. You won't often see this being used on the East Coast. Lastly, let's talk more about weight and damping. As we mentioned previously, the location of mass can have an effect on seismic motion and forces. There are also ways that we can manipulate the motion of our structure to our advantage. The first is through base isolation, which is essentially separating our building from the ground laterally. I've posted an article where you can read more about how this works on Moodle. Finally, we have tuned mass dampers, and I have a short clip for you that demonstrates how this works, as well as a follow-up video on Moodle. So on the left here, you can see we have something like a moment frame, and on the right, we have the same thing, but now we are hanging a mass, in this case a little eraser, from the top of our structure. And now we're going to apply some lateral accelerations, similar to earthquake motion. And as you can see, the structure on the left moves much more drastically than the structure on the right. This is because that mass also has inertia, or resistance to movement. And if we can tune this mass to have the same frequency as our building, then its motion will counteract the motion of our building, reducing both the sway of the building as well as the forces acting in the elements supporting it. Finally, as with our wind discussion, I also want to mention serviceability with earthquake design. With wind design, we talked about the total displacement of the building and provided a range of limits for occupant comfort and durability. With seismic design, we care about the total displacement as well as the drift between stories. And the code gives us limitations for those story drifts here. And we can extrapolate these limitations to give us full building displacement limitations as well. For example, let's consider a case where we are designing a new building next to an existing building. In cases like this, we need to make sure that these buildings do not collide under seismic activity. And so we need to look at the total displacement of these buildings. So, how much separation do we need to guarantee that these buildings will not collide under seismic activity? Well, we know that the drift limit for seismic is restricted to these values here, so we can reasonably assume that the building won't drift beyond these limitations. So we need to calculate our drift limit at 20 feet. And note that we are not calculating the limit at 42 feet. Our new building may sway much more up toward the top, but we don't care about that for now, as that drift will occur above the existing building. So we only care about the drift at 20 feet. So let's say that both buildings fall into this all other structures category. And let's say that both are risk category 1 or 2. The majority of buildings will be in either of these two categories, 1 or 2. 3 and 4 are primarily reserved for large hospitals or buildings that handle hazardous waste. So our drift limit is 0.02 times the height. 0.02 times 20 feet times 12 inches per foot. And so that gives us an allowable drift of 4.8 inches at the top of this building. First, I'd like to point out how much higher our drift limits for seismic are than they were for wind. This is because severe earthquakes that would cause this kind of motion are few and far between compared to wind. And with earthquakes, we expect to feel some motion, and we expect that the building will sustain some damage. Also, if we tried to control the drift and make it super tight, we would be increasing the stiffness of the structure and increasing the chances for more damage, as we discussed. So we will allow for a larger displacement under seismic motion compared to wind. So, are we done? Is this our separation distance? Well, no. This would be our separation distance if only one of these buildings were to move. However, both of these buildings will move under seismic loading, and it's possible that they will move out of sync with one another. So there's a possibility that both will move toward each other. And so if we look at our structural separation section in ASCE 7, we see that they give this equation for separation between adjacent structures. And it's important to note that a structural engineer would calculate the actual drift of both structures to use in this formula. But for this course, we will assume that the structural engineer has designed the building to its drift maximum, and that will be our worst case scenario that we design for. So let's look at this formula. We have our two drifts for our adjacent structures. Both are going to be equal to our maximum allowable, 4.8 inches. And so, to calculate our separation, we simply plug into our formula and we get 6.8 inches. And so that will be our separation between the two buildings. Again, the structural engineer may be able to tighten up this value with additional analysis, but this is a good starting place for us. And so we will wrap up our discussion of seismic loads there. In the next video, we will start to talk about structural analysis, beginning by reviewing some principles learned in Structures 1 surrounding static equilibrium.